Okay, so this is the third of 4 videos on matrix transformations for Math 1410 Linear Algebra, Spring 2017. And this is just going to be a quick overview of a couple of things we've done, and in particular, a generalization of something we saw in the last video, which is that for a transformation of the plane, for a matrix transformation from R2 to R2, if I only know the value of my transformation on the basic unit vectors, I and j, 1, 0, and 0, 1, then I can reconstruct the matrix used to define that transformation. This turns out to be something that's true in general. If I know the value on sort of my basic unit vectors, whatever the dimension happens to be, that's enough to figure out my matrix transformation in general. Right? So recall that for any linear transformation t going from Rn to Rm, the two rules that it has to follow are that t of x plus y has to equal t of x plus t of y. So this is true for any x, y in Rn. And 2, if I have any scalar c in vector x, I can pull the scalar out. Okay, and this is true for any scalar c and any vector x in Rn. Okay, and so one of the things you'll note in general is that if we let, let's call them maybe E1, so E1 being 1, 0, everything else is 0. E2 is going to be the vector with a 0 and then a 1, and then everything else is going to be a 0. So a 1 here, and then everything else is 0, and then so on down to, let's say, En, 0, 0, and a 1 in the last spot. Then if I have any general vector x equal to x1 down to xn, I can write it as x1 times E1 down to xn times En. And if I wanted to calculate t of x, right, using properties 1 and 2, it tells me that t of x is going to be x1 t of E1 down to xn t of En. If I use these properties repeatedly, I can get down to this sort of situation here, right? So it's always true that if I know the values of my transformation on these basic vectors, then I can get the value of that transformation on any other vector. But we can also work out what the matrix is, because remember that the value of t on each of these guys, t of E1, that's going to be the first column of A, t of E2 will be the second column of A, and so on. Okay, so here's an example. I give you a formula for the transformation, right? So I tell you, it goes from R3 to R3, so my input is a general vector x, y, z. The output is more complicated, but we notice that all 3 entries are linear functions of x, y, and z, so I expect that this guy should be linear. I'm going to leave this as an exercise for you guys to check, because it's not hard, but the details aren't going to really fit very well on one slide. So you'd want to check that, for example, t of x1 plus x2, y1 plus y2, z1 plus z2, right? So this would be, if I put in the vector x1 plus the vector x2. You'd want to check that that would be the same thing as doing t of the vector x1 plus the vector x2, and so on. So checking that it's linear is just verifying those two properties from the previous slide, but even for something reasonably simple like this, it's a little bit tedious. Probably the easier way to check is to kind of play a game similar to what we did with subspaces and say, well, you know what, I can write this as x times 2, 1, minus 2 plus y times minus 1, minus 3, 0 plus z times 4, 0, 5, right? Decompose this vector, which depends on 3 variables, into the 3 vectors depending on 1 variable each. And if you kind of reverse engineer this row matrix times column rule from matrix multiplication. Remember, we said one of the ways you can do matrix times column is you form a linear combination of the columns of your matrix. If you kind of back that up, you can work out that what you should get here is, well, you should get 2, 1, minus 2, minus 1, minus 3, 0, 4, 0, 5 times x, y, z. Okay, so we can kind of reverse the steps. Start here, right? Start here, and kind of work backwards. Do the matrix multiplication and confirm that these guys here are in fact equal. And you can just simply do that matrix multiplication. You can see that they are exactly the same. And now that we know it is a matrix now we know it's a matrix transformation, we know that it's linear because every matrix transformation is linear. And that sort of negates the need to do this exercise, to do it manually, right? So you could do it by hand, you could do it by brute force, but it's not really necessary. So the way you can do this, rather than kind of playing around with this sort of algebraic hocus pocus, is you simply, like we mentioned, calculate the value on each basic vector. So t of 1, 0, 0, I put x equal to 1, y and z both equal to 0, and what do I get? I get 2, 1, minus 2, right? And you'll notice I get it here, and I get it there, right? If I do t of 0, 1, 0, what do I get? I put x equals 0, z equals 0, y equals 1. I get minus 1, minus 3, 0. And again, we see that those guys match up. Okay. And finally, if I calculate t of 0, 0, 1, I put x and y equal to 0, z equal to 1. I get 4, 0, 5. And we see that those guys match up, right? So calculating t on basically I, j, and k gives you the columns of your matrix and allows you to reconstruct your matrix A. Okay, good. So here's another example, this time going from R3 to R2. So I've given you the value on I, j, and k. I want to calculate the value of t on some other vector, 2, 1, minus 3. So there are two ways that you can do this. One way that you can calculate this is you can say, all right, so t of 2, minus 1, 3, right? If I take that vector and write it in terms of I, j, and k, that's 2i plus minus 1j plus 3k. And using the properties of matrix transformations, that's going to be the same thing as 2 t of I minus t of j, minus 1 times t of j, plus 3 times t of k. So that's 2 times the vector 3 minus 1, subtract the vector minus 4, 5, plus 3 times the vector 1 minus 2. And if I simplify that, I'm going to get 6 plus 4 plus 3. I get 13. Minus 2 minus 5 minus 6. I get minus 13. Okay. All right. So that's one way to do it. The other way to do it is I just simply construct my matrix, right? So I can say the other way to do it is I simply say, well, T of x is equal to A times x, where what is A? A is, well, these three guys here, they form the columns of my matrix. 3, minus 1, minus 4, 5, 1, minus 2. And then I can check that if I take A and I multiply by 2, minus 1, and 3, I get 2 times 3, minus 1 times minus 4, 3 times 1, so 6, plus 4 plus 3, 13. And the second entry, minus 1 times 2, minus 1 times 5, 3 times minus 2, minus 2, minus 5, minus 6. I get minus 13. The same as before. So either method works, and you can work with whichever one you want to do. If you're simply doing one computation, you might want to stick to the option on the left. If you need to calculate the value of t for several vectors, then it's probably worth your while to first work out what the matrix is, because once you have the matrix, you can then calculate the value of t of x on any other vector.